Hey everybody. Alright, we're going to continue our discussion of toxicology that we sort of started. I'm going to backtrack a tiny bit and mention kind of like a classification system developed for carcinogens, just as a interesting thing, because not every carcinogen is completely validated and with definitive evidence. I mean, there's like probable carcinogens and like confirmed carcinogens, and I just want to mention that classification system. So the International Agency for Research on Cancer has developed a kind of a classification system where they have Group 1 compounds, Group 2A, Group 2B, and Group 3, where they've kind of classified molecules based on their potential as carcinogens. So Group 1 is considered, like what we call molecules, like a Group 1 carcinogen. That is if it's pretty definitive. They say sufficient evidence of carcinogenicity. So these are molecules that it's kind of like undisputed, I guess. Example is benzopyrene. We talked about benzo a pyrene is a class 1 Group 1 carcinogen. Group 2A is basically means it's probable. So like a less definitive characterization. Probable carcinogen. Group 2B is called possibly a carcinogen. So it's a little less definitive as well. Group 3 is called non-classifiable. So these are molecules that the evidence is still a little unclear, so we can say it's uncertain. Okay. So yeah, benzopyrene is definitely a class, a Group 1 carcinogen. Group 2A, we talked about dimethyl sulfate. That's considered group. So the evidence is a little less significant that it's actually carcinogen. We know it alkylates DNA, but that doesn't necessarily lead to cancer, and so it's a little bit of a decreased rating, I guess. All right. What else for Group 1? Let's see. I think we'll show a couple more examples of that. Okay. All right. So that's a little bit on the rating system of carcinogens. Oh, benzene. Yeah, benzene is also a Group 1 carcinogen, so the evidence is fairly substantial for benzene. Okay. A little other note about benzene that I saw. Because it's so carcinogenic, it used to be the amount in gasoline used to be around 20%, and now it's about maybe 1%. Because essentially people realized how toxic it is and easy to accidentally expose yourself to, like when pumping gasoline. So they did decrease the typical levels of benzene and gasoline to about 1%. Another little tidbit about benzene: the American Petroleum Institute, which is like a regulatory, a kind of trade group that deals with petroleum. API sort of famously said, actually in 1948, so a long time ago, it is generally considered that the only safe concentration of benzene is 0. So now, you know, that is not something that's used by regulatory agencies. Like the EPA has their own, like, minimal exposure or maximum exposure guidelines. But I think it's pretty safe to say that you don't want to ingest benzene through inhalation or like in food or water or something like that due to its toxicity. Okay? Alright, so that was a little bit more on benzene. What else do I have? Okay, cool. Alright, so we talked about nitrosamines. I'll just show that again real quick. Nitrosamines. Like dimethyl nitrosamine. NDMA. Oh, actually, yeah, the name of it is I don't know if I told you that. N-nitroso dimethylamine. Right. And so the N-nitroso refers to the top thing, dimethylamine refers to the bottom thing. And we basically showed that it would eventually get metabolized to something like methyldizonium. Which is just a methylating agent and methylates your DNA. Okay, so and this also using that classification system is it's IARC, which is the International Association of International Agency for the Research of Cancer. This was not a group 1, but it was a group 2. So a little less definitive or a little less conclusive on the carcinogenicity. This is a probable carcinogen instead of a known carcinogen. Okay, so that said, let's move to a couple more nitrosamines. We'll say other toxic nitrosamines. They're kind of interesting, and you know, as an organic chemist, I love cool organic structures, even toxic ones. So, what is this molecule? You may have probably seen this somewhere. It's a pyridine with a 5-member ring, nitrogen. There's a chiral center. I'm not going to show that, the chirality of it. But of course, this is nicotine. the mild stimulant found in tobacco. So kind of through the processing of tobacco, this can actually kind of get demethylated, so the methyl comes off and form a different nitrosamine. And the name of this molecule is N-nitrose. N-nitroso. Nor-nicotine. Nor-nicotine. What does nor mean in terms of the structure? So nor is usually kind of means like loss of a methyl. Like the loss of a methyl. So what happens is the methyl gets lost and then it gets replaced with the nitroso group through sort of processing. I don't know exactly how they do that in terms of like making cigarettes and things like that. So what, and then how would like this, just in a nutshell, be like alkylate your DNA, and how would that look? Because we saw how dimethyl, the nitrosodimethylamine did it through formation of this kind of highly electrophilic diazonium salt. So one possibility is, and you can review how we described that in the last lecture. It was basically hydroxylation of of the methyl group, and then it sort of falls off, and then we got some proton movement around to kick off the oxygen, and then you basically get the diazonium, and that does the bad stuff. Okay, so something like that probably happens with nitroso-nor-nicotine. As also, the abbreviation is called NNN. NNN. Okay, so probably hydroxylation of the benzyl position, which is next to the, what's his name of this heterocycle called? On the left is a pyridine, right? So nicotine has a pyridine in it. 5-member ring with a nitrogen is called a pyrrolidine. So you have a pyridine and a pyrrolidine in this molecule as well as nicotine. Okay, so we're going to oxidize with P450 this position, the CH next to the pyridine. And that gives you a hydroxy group. And that position is kind of activated by the fact that, without going into P450, it likes to make like radicals. So there's a radical intermediate, and the radical being next to the pyridine, which is an aromatic ring system, is actually kind of happy. So that position is most likely to be oxidized as opposed to like that position, because they could both get oxidized, but that one's going to be a little more likely. And if that happens, let's draw what kind of happens next. The oxygen can kind of kick down and in. And then break this off. So it opens the ring up. So the oxygen kicks in, opens up the ring. What does that give us? Kind of like AR for aromatic. Now you get a ketone. because that creates a ketone. How many carbons? 1, 2, 3 carbons in the nitrogen. 1, 2, 3 carbons, then a nitrogen, H. I'm going to draw it this way. And the nitroso. Okay? See how that formed? Oxidize, and then it kind of opens up the ring. Now you have a ketone, and you have a nitroso thing. And basically at this point, we do the same kind of processing that we saw for the dimethyl, or the nitrosodimethylamine. And so essentially, a little more happens. You lose N2, and then DNA is just kind of attached to this, which DNA doesn't like to attach to random molecules, and that would lead to the mechanism of carcinogenesis. Okay, so this molecule, it's funny because the dimethyl, this one up top, we said is a group 2A probable carcinogen. This one actually went a little further in terms of the evidence. So the IARC calls this a actual group 1 carcinogen. Which is a known carcinogen. So they have a little more evidence. Human carcinogen. I'm not sure what, how they established that and what the difference in data is. Just one more while we're on this theme of toxic nitrosamines. The diethyl version is just this. Because we did dimethyl. Yeah, well, the diethyl one's actually known also. This is N-nitrosodiethylamine. Abbreviated NDEA. And it does the same kind of processing to eventually give you DNA with an ethyl group on it. So probably hydroxylation, kick off, cleave a bond, cleave that bond. So hydroxylate, cleave off the bond, and then you get basically that, right? And it does the same kind of processing of the nitrogen and make a disonium N triple bond N thing, and then DNA would put attached to that. This molecule, interestingly, is also found in tobacco smoke. I don't think it's found in food, but I'm not too sure. Also in tobacco smoke. Another example of something from tobacco smoke. Nicotine makes, I think, the most sense because, well, nicotine is present in pretty high concentrations in tobacco, and this mechanism makes a lot of sense. Okay, cool. And then curiously, this is back to that IIRC ranking, a group 2. Carcinogen, and by group 2 they mean it is probable. So yeah, there's probably some detailed data how they established this. It is kind of curious, one nitrosamine. Well, we have a couple nitrosamines that are group. It's 2A actually. 2A was the probable ones. We have a couple of the nitrosamines that are group 2A carcinogens, and then like this other one is group 1. So there must be some difference in the data. Okay, cool. So that is it for nitrosamines for now. Another kind of cool, interesting topic, say an example of toxic substance, but this is kind of a little bit of nuance to this one. So sodium nitrite. I don't know if you've heard of this story before. Sodium nitrite, which is Na plus O minus, so 3 lone pairs, and double bond O lone pair, so sodium nitrite. Is it's found in foods and in foods, and also used as a preservative. So it's added to foods and preserved foods. Most commonly, it's known in processed and preserved meats. Things like hot dogs, bacon. It's frequently found in bacon. You often see this like on the list of ingredients. Interestingly, it is found in like smoked turkey, all sorts of kinds of smoked turkey. If you read the label, you'll see nitrites, sodium nitrite, but not like more fresh, less processed turkey like deli turkey. That's interesting because I do eat turkey, and I've kind of looked at the labels, and yeah, deli turkey is frequently not processed or preserved with nitrites, but almost all smoked turkeys have nitrites in them. Okay, so what's the big deal about nitrites? And another interesting thing about nitrites. Sometimes, celery powder. Celery powder has concentration of nitrates and nitrites. And sometimes, because of that, and celery powder is considered like a natural substance. Sometimes meats are packaged with celery powder as kind of a way to disguise the fact that it actually contains nitrites. So sometimes meats are packaged with celery powder. You could call that nitrite in disguise. Okay, so what is the issue with nitrites as potentially a toxic substance? And it's actually we'll see that it's basically going to be used as a reagent to cause the formation of those nitrosamines that we were just talking about, which is kind of weird. Okay, so how does that work? Okay, so what sodium nitrite does, it's Na plus O minus, is it gets, it reacts, we'll say, with proton times 2. So the oxygen, the O minus, will get doubly protonated, and you get OH, H, and double bond O, plus charge on oxygen. And then the oxygen will swing in and kick off that water. And that makes nitrosamine ion. With a plus charge on oxygen. Okay, nitrosamine, nitrosium, I'm sorry, nitrosium ion. There's no amine there. Nitrosium ion. Okay, so then this is actually a source for the nitrosa group. So then, in a lot of amine, or sorry, a lot of meats and things like that, there's amines, and amines, of course, are kind of fishy-smelling substances. They just there's a lot of amines in all sorts of kinds of meat and fish and things like that. Okay, so basically, these are present in the various meats and things that are being preserved, and so the now dimethylamine will actually attack this thing and push electrons, break the triple bond and push electrons onto the oxygen, and that actually gives you a source. This is like kind of where nitrosamines, one of the ways that nitrosamines are actually created. They're also, I think, created through the cooking process and other things. So there's a lot of sources of nitrosamines, but this is definitely a big one. It's basically from nitrites. Okay, and then this thing is what we were just talking about a second ago. So this will create that methyl diazonium thing again and lead to alkylated DNA. Okay. Okay, so kind of wrapping up the discussion on sodium nitrite and nitrosamines that can form. So there is some controversy on the whether or not sodium nitrite is actually, you know, causes this in food, and the actual reaction of sodium nitrite and amines to make nitrosamines, that's pretty well established. But whether or not this actually happens in your body to produce significant concentrations of these carcinogens is still a little up for debate. It's just because it's you know, in any kind of an organism like a human, it's a little hard to establish things like this. It is a controversial topic. There's a lot of lobbying by groups, maybe related to the food industry, that you could arguably have a financial stake in this debate. Why would they have a financial stake? Well, because if they, you know, by adding preservatives, you can preserve food, and you can actually, and by food lasting longer, they basically make more money, is the thought, right? By food groups. It's still, it is controversial, and there's definitely kind of people that argue both sides of this. And I do have a review article that seems to be a pretty fair discussion about this if you're interested in it. It's a balanced review of the pros and cons of using nitrites in food and like cured meats and things like that. Journal is Antioxidants. year 2020, so semi-recently. Volume 9, issue 3, page 241. So there's a discussion about this and maybe some of the, a little more on the controversy. I should also say, you know, even though nitrites may be creating these nitrosamines, if there was a cancer risk associated with nitrites, you know, that does take a long time to establish. So cancer risk, if there is a cancer risk in foods, would take a long time. And also, remember that mutagenesis, so we'll just say a little bit of alkylated DNA, does not always translate to carcinogenesis or cancer. Okay. So those are a couple other points. And then there's one more interesting thing, that adding vitamin C, ascorbic acid, actually kind of can prevent the reaction of nitrosium to make nitrosamine. So I'll show that briefly on the next page. Okay, so just repeating what it has said, you can add ascorbic acid, vitamin C, to sort of block the formation of nitrosamines. How does that work? What is vitamin C? So vitamin C is, we got an alcohol, secondary alcohol, hydroxy group, okay, that's vitamin C, ascorbic acid. So also another thing is that nitrate, which is another ion, it actually gets converted to nitrite, which is the kind of the bigger concern. This happens through bacteria in the stomach and the gut. So gut bacteria do this. I think nitrate, if I remember, is NOOO, something like the nitrate. I'm gonna check real quick. Yeah, that's the right structure for nitrate. So nitrate and then nitrite is basically that, right? So nitrate is actually also found in like celery powder, and it basically gets converted to nitrite with gut bacteria, and then that forms that thing called nitrosium. So the sort of the bad chemical that actually causes nitrosamine formation, plus charge, right? Anyway, this is an oxidizing agent, and this can oxidize ascorbic acid, and then you basically form, after all of that, it gets reduced to nitric oxide. Nitric oxide is a weird molecule in terms of the chemical structure, because it, as drawn, it would be positively charged, but it actually has an extra electron there, so it's actually a free radical. Nitric oxide is a free radical. Okay, so it is a kind of biological signaling molecule. Biological signaling, and it has various effects in the body, but the big thing is it's not a carcinogen, and it doesn't have any of the bad effects that nitrosium does. So this being a result, or like a product of nitrosium, I'll write nitrosium up here. That's that thing again. N triple bond O plus is nitrosium. So nitric oxide being a product is actually kind of a good thing, because it's not toxic the way nitrosium ultimately is. And what happens to ascorbic acid is it gets oxidized to a diketone. Molecule that looks like that. So it's kind of acting like as a scavenger for nitrosium. Yeah, the name of the molecule, this molecule, because it lost 2 hydrogen atoms here, is called dihydroascorbic acid. Okay. I think so. I am basically at this point we're done with the toxicology, toxicology discussion. And we have a lot more pharmacology stuff to get to. That's going to be wicked. I can't talk. That's going to be done with PowerPoint, and I think I'm just going to stop this lecture now, and I'll just continue the PowerPoint in the next synchronous lecture. It'll be probably a good transition point. Alright, so I'll talk to you guys in a couple days.